So before starting, I would like to acknowledge my co-authors and also the other institution that contributed to this work, SINTEF Industry, and also the Federal Institute of Material Research and Testing, BAM, in Berlin. This is a joint study that has been conducted by NTNU and the other two institutions. So going directly to the content of the presentation, first of all, I will very briefly introduce the issue of hydrogen embrittlement and how the interaction between steels and hydrogen can compromise their durability over time and their mechanical performances. After that, I will briefly talk about the testing technique we have to assess the influence of hydrogen on the mechanical properties of steels, focusing mostly on autoclave testing and the hollow specimen testing technique that has been also introduced by the previous contribution. After that, I will talk about the materials we have investigated, so an X65 pipeline steel, and also the methodology we have used. After that, a more detailed discussion about the results we have obtained, focusing on the stress strain curves, but also the embrittlement index and brief fractographic analysis. And finally, some take-home messages and the summary of the results and some ideas for future works. So as it was told before, hydrogen embrittlement is an environmental degradation that consists in a loss of mechanical properties and particularly tensile properties that result from the ingress of hydrogen atoms within the metal lattice. So basically this physical phenomenon relies on the synergistic interaction of many factors. So although it has been widely studied in the past, it has not been fully understood so far. So it relies on the effect of the environment that should contain hydrogen, of course, and more particularly on the temperature of the operating environment, but also the pressure and the hydrogen purity. We need a susceptible material. So the material could be susceptible or not based on its chemical composition, microstructure, and also strength, but also the presence of internal defects. And finally, the presence of mechanical load. In this case, considering that we tested with slow strain rate tensile test, we consider the strain rate, but also the presence of stress concentration that could result from notches or pre-existing defects. All these parameters are crucial for the material susceptibility to hydrogen embrittlement. So they should all be thoroughly evaluated when it comes to, let's say, evaluate the suitability of an existing infrastructure for hydrogen transport and storage. From a more engineering perspective, there are only a few standards available for the design, inspection, and maintenance of industrial equipment that are exposed to hydrogen or normally operate under hydrogen environments. So the lack of a unified regulatory framework results in over-conservative design criteria and a limited choice of steels that could be used for hydrogen service. Moreover, it is particularly interesting from an engineering point of view to retrofit the existing pipeline network in order to use it for transporting various amount of hydrogen, either pure or blended with natural gas. But in order to do so, we have to thoroughly evaluate the impact that hydrogen atoms have on the structural integrity of the pipelines. So in order to test the effect of hydrogen environments on the materials, we have several techniques. They could be either ex situ or in situ testing. But when it comes to ferritic steels, we basically rely on in situ testing, charging with gaseous hydrogen in order to mimic the actual environmental condition of a pipeline. And we can use either an autoclave filled with high pressure hydrogen or a more, let's say, novel and unconventional technique that consists of using hollow specimen as a containment volume for pressurized hydrogen. I will not go in depth because it has been already explained, but I will briefly summarize some advantages of the first technique and the second one. Autoclave testing are a well-established testing technique. So it is standardized and we have clear indication regarding the testing condition, but also the geometry of the specimen. On the other side, this technique is very expensive and it involves very high safety regulations because we are handling highly flammable fluid under high pressure. So basically, a hydrogen autoclave is extremely dangerous and should be properly handled by highly specialized personnel. So this technique is very complex and difficult to maintain, and it also has long overall test duration. So all this limitation reduce the testing capability of a laboratory. So in order to overcome all this limitation, we also use the holospecimen testing technique. On one side, it has not been standardized because it is relatively novel. Therefore, it is very difficult to compare the results of previous results obtained with conventional tests with the new results obtained with holospecimens. But in this case, as it was mentioned before, the sample itself acts as an autoclave and mimics the conditions of a pipeline or a tank. In this case, only static sealings are necessary to isolate the specimen. And therefore, this technique is way simpler to handle and reproduce compared to autoclave testing. It has a shorter overall test duration and very limited costs. I cannot go in depth on this point, but there is an order of magnitude of difference in costs for each test. So it is extremely noticeable. We have tested a different steel. It is also pipeline steel, but in this case, a vintage X65 pipeline steel that was manufactured by Fukuyama Steel Industries in 1982 and used for around 40 years for natural gas transport subsea. It is a Norwegian subsea pipeline. It was extracted by a Norwegian subsea pipeline. From the base metal of this pipeline, from the mid-thickness in the longitudinal direction. The chemical composition was measured by optical emission spectroscopy and is coherent with the specification of the standard API 5L. The microstructure was also investigated, and it is composed of polygonal ferrite and perlite in banded appearance, but there are also plate-like beneath bands in the direction of the rolling. We have also measured through strain rate tests the yield and ultimate tensile strength. And basically, we figured out that this banded microstructure could result in a highly anisotropic mechanical behavior of the specimen tested both in air or argon and in hydrogen. But we will talk about it later. So the specimens were manufactured in different ways because we have both holospecimen and solid specimens. In the case of holospecimens, we have used two different manufacturing techniques in order to evaluate the impact of inner surface roughness on the susceptibility of the steel to hydrogen embrittlement. The first type of steel was manufactured by conventional drilling, and the second by drilling and greening in order to obtain a smoother surface roughness. On the other side, the solid specimens were manufactured by conventional turning in order to obtain the same gauge diameter of the holospecimen and have somehow comparable results. Unfortunately, we weren't able to obtain exactly the same roughness of the rimmed specimen on the external surface of the solid ones, but we tried our best to achieve a similar surface roughness in order to have comparable results. So, considering the testing techniques both in the autoclave and with holospecimen, we use the same hydrogen purity, which is a grade 5 hydrogen. And we try to obtain a very low oxygen content because oxygen is well known to be an inhibitor for hydrogen embrittlement. So we purged 6 times from 10 bars to 60 bars in order to achieve the desired oxygen content within the autoclave and within the holo of the holospecimen. And also the tests were conducted at room temperature with the same nominal strain rate of 10 to minus 6, so very slow strain rate. And in the case of the autoclave, the sensor were able to monitor online the presence of hydrogen, so we can guarantee that the nominal testing conditions were kept constant during the entire duration of the test, which is approximately 3 to 4 days for tests conducted in hydrogen. Regarding the results we have obtained after this testing campaign, we evaluated the impact of hydrogen on the tensile properties using a well-known index that is known as embrittlement index. It is defined as the ratio between the reduced area fracture measured in reference environment. In this case, we used argon in the case of holospecimens and air for the tests in autoclave, minus the reduced area factor in hydrogen divided by the reduced area factor in the reference environment. So the higher the embrittlement index, the higher will be the impact of hydrogen on the tensile properties of the steel. In the graph on the right-hand side, you can see that the tests were conducted with all the specimen, either drilled and reamed at 60 bars, and also at 60 bars with the solid specimen, but we have conducted other tests with solid specimen at higher pressures, up to 500 bars, in order to exploit as much as possible the capability of the autoclave. And we can see that even if the embrittlement index obtained with the drilled and reamed specimen and conventional specimen is basically uncomparable, because the geometry of the specimen is way different, we can see that the higher the pressure of hydrogen in the autoclave, the higher will be the embrittlement index. So we don't see any saturation effect up to 500 bars. And this is quite interesting, because increasing the pressure of hydrogen within the pipe, we will also increase the susceptibility of the steel. So we have a continuous degradation as we increase the pressure. As you can see from the table in the bottom part of the slide, the drilled specimen have a relatively higher, well, a higher average embrittlement index compared to the reamed specimen. So apparently the surface roughness has a substantial impact on the hydrogen embrittlement susceptibility. Considering here the stress strain curves obtained in a hydrogen environment, we can see that the drilled specimen manifests a significant elongation loss, while the elongation loss for reamed specimen is lower. And also there is a lower scattering for the reamed specimens that are depicted with the blue lines compared to the drilled specimen in red lines. The black line is for the conventional test conducted with a solid specimen, which is basically the average of the other tests. On the other side, the stress strain curves obtained in argon, so the reference environment, show a very limited scattering for both the drilled and reamed specimen. So there is no substantial impact on the surface finishing when it comes to evaluate the tensile properties in inert environment. While there is a difference for the solid specimen that is mostly due to the completely different geometry we have in this case. Going to the fractographic analysis in hydrogen, we can see moving from the left-hand side to the right-hand side, the test conducted with a solid specimen, the test conducted with a hollow drilled specimen, so with the higher roughness, and on the right, hollow specimen in reamed configuration. And we can see for all of them, we have a very limited necking, and also 3 different zones. The first one, the closer to hydrogen, is a brittle zone characterized by quasi-cleavage fracture. Then there is a transition zone. And finally, in the part that is far from the exposure to hydrogen, a ductile zone characterized by microvoid coalescence. Going to the higher magnification, we can clearly see the presence of quasi-cleavage fracture in the outer area of the solid specimen and in the inner part of the hollow specimen, so the closer part to hydrogen. While there is a transition zone that is characterized by the presence of both dimples and intergranular cracks that shows how hydrogen permeated up to a certain part of the specimen in the radial direction. And we figured out, considering the portion of quasi-cleavage fracture and microvoid coalescence, that basically surface defect has a strong impact because they can act as a crack initiation site. So the fraction of quasi-cleavage fracture is way higher in the case of drilled specimen. Considering the test in a reference environment, moving from the left-hand side to the right-hand side, we can see that the solid specimen show a noticeable necking and an elliptical fracture surface that result from the anisotropic mechanical behavior due to the microstructure of the steel. But we can see the same elliptical fracture surface, even if with lower necking, also for the hollow specimen in drilled and reamed configuration. Going to the images obtained with a higher magnification, we can see basically no difference between the test conducted with solid and hollow specimen. So all of them manifest dimples, indicating a ductile behavior. And also there is no difference between drilled and rimmed, as I mentioned before. And this is also reflected by the fractographic analysis, not only the stress strain curves. So basically we can conclude that the surface finishing has a strong impact when it comes to evaluate the influence of hydrogen on the mechanical properties, but it has not substantial impacts in inert environments. So in order to summarize the main results of this research, the scope of the overall study was to compare the tensile properties in high-pressure hydrogen environments obtained with a traditional in situ testing technique, so using the autoclave, and the more novel hollow specimen testing technique. And for all these tests, we figured out that the tensile properties of vintage X65 pipeline steel with banded ferritic and perlitic microstructure are significantly degraded by pressurized hydrogen gas. So the existing Norwegian pipeline network could be repurposed for hydrogen transport, but with lower pressures for sure, so lowering the operating pressure of the pipelines. And also for all these specimens, we figured out that there is the presence of a quasi-cleavage brittle region, a microvoid coalescent ductile region, and also a transition zone in between. In the future, we will evaluate the different stress fields in hollow and solid specimen in order to better understand the physics behind these tests and to better understand how this stress field impact the susceptibility of the material and of the steels under different testing conditions. So thank you for your attention and time. That's it so far. If you have any question, I'll be very happy to answer.